Welcome back. This is topic 26, multilayer perceptrons and activation functions. Last time we found the edge of what the single neuron can do. Today we go past it and the whole topic turns on one idea, non-linearity. 4 parts. First, the structure of a multilayer perceptron. Second, why a nonlinear activation is not optional but essential. Third, the activation functions themselves. And fourth, the vanishing gradient, the problem that decides which activation you actually reach for. Last topic ended on a cliffhanger. A single perceptron cannot solve XOR, but a multi-layer perceptron with one hidden layer solves it instantly. That left 2 questions hanging. The first is how does a hidden layer do something a single neuron probably cannot? The second is what function sits inside each neuron, the activation function, and why does that choice matter so much? Here is the punchline before the proof. Most answers turn out to be the same one word, non-linearity. Start by remembering exactly where we left off. We proved a single neuron cannot do XOR, and then we built a network that can, by hand, out of 3 ordinary neurons. The first hidden neuron computes a war. It fires when at least one input is on. The second hidden neuron computes NAND, which is not AND. It fires unless both inputs are on. And the output neuron computes AND of those 2. Notice the shape of this. 2 neurons sitting in a hidden layer and 1 neuron reading their answers. Today, we give that chip its name and we answer the 2 questions it left open. This is a multi-layer perceptron, an input layer, 1 node per feature, then 1 or more hidden layers, then an output layer. Every neuron connects to every neuron in the next layer, which is what fully connected means. The hidden layers transform the features, and more layers let the network learn more intricate patterns. Look closely at 1 layer. A single neuron takes the previous layer's outputs and returns 1 number, a weighted sum, plus a bias, passed through an activation. A layer is just many neurons reading the same inputs, stack their weight rows into a matrix W and their biases into a vector B, and the whole layer is 1 line. H equals phi of Wx plus B, with the activation applied to each entry. That 1 line is the entire network, repeated layer after layer. If you can read that line, you can read any feed-forward network, no matter how deep. Let us make it concrete and run a forward pass with no computer at all. A network with 2 inputs, 2 hidden neurons, and 1 output. Here are the hidden weights and biases, and the activation is a simple step. Feed in the input 1, 0. Multiply the weights by the input and add the bias. The first neuron scores positive 0.5. The second scores positive 0.5 as well. And the step function turns each into a 1. So both hidden neurons fire. The first is OR and it gives 1. The second is NAND and it gives 1. Nothing here is new arithmetic. A forward pass is just this one layer at a time. Now the central question, why do we even need the activation? Suppose we dropped it and stacked plain linear layers. Layer 1 computes W1x plus B1. Layer 2 takes that and computes W2 of it plus B2. Substitute the first into the second and everything groups. Two linear layers collapse into a single linear layer. The combined weight is W2 times W1. The combined bias is 1 vector, and that is it. 10 layers would collapse the same way. So without a nonlinearity in between, any depth at all still draws one straight boundary. That is exactly the perceptron we already proved gets stuck on XOR. The nonlinear activation between the layers is the thing that stops the collapse. Take it out, and the depth is an illusion. If the algebra felt slippery, watch it with real numbers. Give the two layers actual weights, still with no activation between them. Multiply them out. The two weight matrices become one weight matrix, this one. Two layers, 6 weights, and the network computes exactly the same thing as a single matrix times X. The depths bought nothing at all. That is why the activation cannot be optional. Here is the same point as a picture. Two identical networks on the same 4 cluster data. On the left, with no activation between the layers, the best it can do is one straight line, and it gets about 52% right, barely better than a coin. On the right, the very same network, with a ReLU between its layers, bends the boundary around the clusters and reaches 100%, same depths. The activation is the entire difference. So what is the hidden layer actually doing? It remaps the inputs into a new space where the problem becomes linearly separable, and then the output neuron draws its one straight line in that new space. The slogan for the whole course is on this slide. Hidden layers learn a representation in which the answer is simple. Let us watch that remap happen on XOR by hand. Use the hidden layer from before. The first neuron is OR, the second is NAND, and for each of the 4 inputs, read off its new coordinates, the pair H1, H2. Start with the input 0, 0. OR is 0. NAND is 1. The input 0, 1 OR is 1, NAND is 1. This is an XOR 1 point, the input one. 0 OR is 1, NAND is 1 again. The other XOR 1 point, and the input 1, 1 OR is 1, NAND is 0. Now look at what happened. The two XOR1 inputs, 0, 1 and 1, 0, both landed on the same point, 1, 1. In the new space, the 1 class is a single corner and the 0 class is the other two corners. And one straight line splits them cleanly. That is the whole trick of a hidden layer. On to the activation itself. There are 4 you will meet again and again, and each has a personality worth knowing. Sigmoid squashes any input into the range 0 to 1. It is our old friend from logistic regression, and it is natural when you want a probability. Its weakness is that it saturates for large positive or large negative inputs. It flattens out. 10 is the same S shape, but it ranges from -1 to 1, and it is zero-centered, which tends to train a little better than sigmoid. It still saturates at the extremes. Real just zeroes out negatives and passes positives straight through. It is cheap, and it does not saturate for positive inputs, which is why it is the default for hidden layers. Its one flaw: a neuron stuck on negative inputs outputs 0 forever. A dead neuron. Leakyville fixes exactly that. It leaks a small slope on the negative side instead of a flat 0, which keeps every neuron slightly alive. A cousin called probably goes further and learns that slope. Saturation is not just a word, so let us put a number on it. The slope of sigmoid is sigmoid times 1 minus sigmoid. Right in the middle at input 0, sigmoid is 1/2. So the slope is 1/2 times 1/2, which is 0.25. That is the largest slope sigmoid ever has. Now go out to input 6. Sigmoid is about 0.9975, so close to 1 that 1 minus it is tiny, and the slope is about 0.0025, 100 times smaller than it was in the middle. So far from the center, the output is almost flat, and its slope is almost 0. A neuron that saturates passes almost no gradient backward. Hold on to that number 0.25 because the next section is built on it. Here is the dead neuron in slow motion. Suppose a real neuron's weights push its pre-activation negative on every single training point. Its output is then the maximum of 0 and the negative number, which is 0 every time. On the negative side, the slope of Wilu is 0, so no gradient reaches its weights at all. And with no gradient, the weights never change, so the pre-activation stays negative forever. The neuron is dead. It will never contribute again. This is exactly what leaky ReLU prevents. By leaking a small slope on the negative side, a little gradient always gets through, and the neuron can climb back to life. Now we can say why ReLU took over from sigmoid and tan in deep networks. Training works by backpropagation. Next topic, and backprop multiplies activation slopes together, one factor for each layer. Sigmoid slope never exceeds 0.25. So across 8 layers, the gradient shrinks to about 10 to the minus 5, and the early layers stop learning. Middle slope is exactly 1 for positive inputs, so the gradient flows through intact. Put the numbers in. The backprop multiplies 1 slope per layer, and with sigmoid, the best case is 0.25 at every layer. Over 8 layers, that is 0.25 to the 8th power, which comes out to about 1.5 times 10 to the minus 5. And remember, that is the optimistic figure. 0.25 is the best sigmoid ever does. Away from the middle, every factor is smaller, so the real product is even tinier than that. ReLU could not be more different. Its slope is exactly 1 for positive inputs, and 1 to the e to power is still 1. The product does not shrink, and the gradient reaches the deep layers intact. But single fact is most of why deep networks became trainable. And here is the whole topic in a few lines of PyTorch. A sequential model, a linear layer from 2 inputs to 8 hidden neurons, a ReLU, then a linear layer from 8 down to 1. It is the same neurons as topic 25, with 1 and n dot ReLU between the layers. Everything we said today is captured by that one line in the middle. A simple rule of thumb covers most cases. For hidden layers, use ReLU or leaky ReLU. By default, cheap and no vanishing gradient. For the output layer, match the task. Sigmoid for binary classification, softmax for multi-class from topic 23, and no activation at all for regression when you just want a raw number. Let us recap. A multilayer perceptron stacks fully connected layers, and the hidden layers transform the inputs into new, more useful features. Without a non-linear activation, stacked layers collapse into a single linear layer, one straight boundary. The non-linearity is what lets depth build curved boundaries. A hidden layer solves XOR by remapping the inputs into a space where a single line separates the classes. And on activations, sigmoid and tan saturate and cause the vanishing gradient, while ReLU, whose derivative is 0 or 1, avoids it. Exactly how a network computes all those gradients layer by layer is backpropagation, and that is the next topic. See you there. 왔어.